Hello, thank you for joining me. My name is Matthew Hasenjager. Currently, I'm a postdoc at the University of Tennessee, Knoxville. But today I'd like to share with you some of my work on self-organization within Honeybee forager networks that I carried out as part of my previous postdoc at Royal Holloway, University of London. So a general problem that's faced by many social groups is how to coordinate the actions and behaviors of its individual group members in order to achieve some beneficial collective outcome, whether that might be winning the soccer match or maintaining cohesion as part of a moving animal group. And a key element in shaping collective outcomes is a group's social network, as it's through this network that individuals can share information with one another and respond appropriately. And this also raises the possibility that by altering its social connectedness, a group might be able to regulate its collective outcomes. So for example, social insects often achieve this through the architecture of the nest itself. So for instance, in honeybees, there's a region of the hive known as the dance floor. It's immediately adjacent to the nest entrance and exit. And foragers tend to congregate on the dance floor. And as a result, there's a concentration of foraging-related information within a relatively small region of the nest. However, even within this small area, there can be multiple groups of foragers that are collecting from different flower species and from different flower patches. And so what we were interested in this study is how are interactions structured within and between these different forager groups? And if they are structured in some fashion, what might be the consequences for collective foraging? And here we're specifically interested in the potential role of floral cues in structuring these forager networks. So honeybees are very adept at learning to associate floral odors or other odors with nectar rewards, whether they're experiencing these food odor pairings at the flower itself or indirectly in the hive through different forms of social interaction. And so by cueing in on foragers that smell like a particular flower species, this might provide a way for honeybees to rapidly gain up-to-date information about the current profitability of different flower species. So in the study, we had two main objectives. The first being investigating whether honeybee interactions within and between these different forager groups are organized according to scent. And if they are, then what are the potential consequences for collective foraging, focusing in particular on the reactivation of experienced foragers to sites they've previously visited. So to do this, we carried out a series of experimental trials, and we would train up groups of foragers to paired feeding stations where each station provided a unique scent. So one station might provide a geranium scent and the other station might provide a peppermint scent. And so different forager cohorts learn to associate these scents with their particular feeding station. And we then interrupted foraging for a time before reinstalling the feeders and observing the reactivation process. So during a trial, we would record the order in which our individual bees returned for the first time to their familiar feeding stations. And during this reactivation process, we recorded all of the interactions that were occurring on the dance floor within and between these two forager groups, focusing in particular on three types of interactions that are involved in the communication of foraging information. So that would be the transmission of resource locations via waggle dances, food sharing during trophallaxis, and the antination of returning foragers. So we took these records of interaction and we built up the corresponding interaction networks for each one. And so to address our first objective in terms of how are these networks structured, we measured the assortativity of these networks according to scent. And when we did this, we found strong evidence of positive scent-based assortment in both the dance following and antination networks, though not the trophallaxis networks. So here is depicted one of the networks from these trials. This is a dance following network, and hopefully what you can see here is that there are many more connections between same colored nodes, and those connections tend to be stronger. And here the different colors of nodes correspond to the different scents that were provided at the feeders themselves. So what this analysis tells us is that not only were bees able to differentiate between the two scents coming into the hive on the bodies of foragers that were returning from these feeders, but that they interacted more often and they interacted for longer with bees that came in smelling like the resource that they had previously visited themselves. So next we wanted to investigate the potential consequences of this scent-based assortative mixing on the spread of foraging information. And to do this, we turned to a technique known as network-based diffusion analysis, or NBDA. And the idea of NBDA is that it quantifies the importance of social information flow in the diffusion of a behavior through a group. So specifically what we can do is look at the order in which individuals reactivated to their familiar feeder and map this onto our measured interaction networks to compare the relative contribution of these different interaction networks in driving these reactivation patterns. But we took this one step further. We split each of these three networks into two more networks where we differentiate between interactions that occur between individuals trained to the same feeder, so we'll call those same scented interactions, and interactions between individuals trained to different feeders or different scented interactions. And this allows us to evaluate the importance of that scent-based assortative mixing that we found earlier. So what the NBDA found is that overall, there were substantially more reactivation events were explained by same scented interactions than different scented interactions. However, even though the assortativity analysis found that individuals were able to distinguish between these scents, and that they preferentially interacted with bees that smelled like their own familiar feeding site, we found no real difference in the contribution of same versus different scented interactions for the trophallaxis or antination networks. And these are the two networks that we would expect to be primarily involved in the transmission of olfactory information. However, when we look at the dance following networks, we find that substantially more reactivations were explained by same scented dances than different scented dances. And what this suggests is that even though foragers knew the location of their familiar feeding site, that they still were paying attention to the spatial information provided by dances, so that when this social information matched up with their own private navigational memories, foragers were especially likely to reactivate. So to briefly summarize, we found that even brief exposure to scented feeding stations led to positive scent-based assortative mixing on the dance floor, and as a result, substantially more reactivations were explained by within cohort than between cohort interactions. So through the formation of these resource-specific cohorts on the dance floor, this could aid individual and collective foraging efforts by helping bees to rapidly gain up-to-date information about familiar resources in their environment. So before I end, I just want to take a moment to thank my co-authors on this work, Leadbeater and Will Hoppitt, all those who helped me with carrying out the experimental work and watching the videos, as well as our funding sources. And thank you so much for your attention. I'd be happy to take any questions you might have.